Hello, this is a AQA A2 video. Now, physics obviously. What we're doing in this video is we're going to be talking about Coulomb's law, Charles Columb. Oh, I can't say his name anymore. Okay, so in the last video, just to recap, we looked at electrical potential, which was 5.3 in your AQA book, and in that, the last thing we mentioned was the gradient of the electric equipotential is equal to the negative of the electrical field strength. Something else we mentioned in that video, that the equipotential gradient is the potential difference over D. So they were the last two sort of main things in that. We also talked about what electrical potential was, and it was Q times V. So charge times potential difference, and it's the work done per positive unit charge. That's what we said. Okay, so that was a recap of 5.3. A recap of 5.2. So this is going back a little bit now, recapping a bit more before we start this. In 5.2, we talked about electrical field strength. We said the electrical field strength was a electrical force per unit charge, over force over charge. And then we mentioned about the, remember the circuit diagram, where we said we incorporated that idea, electrical field strength is force per unit charge, rearranged it to get force, put that into work done across a distance that we had of two potentials, and then we just applied that and sort of put a bit of emphasis. 5.1, the very start of this chapter, we just talked about opposites attracting, and that's actually what we're going to start with in this chapter. Okay, so Coulomb's law, right, I'm not going to go into too much detail at the moment, just a brief introduction into this part of the topic. We should know that obviously you have your opposites repel and your likes attract. Now that doesn't just happen out of circumstance, that's representative of a force that's in there. Now, Charles Columb thought, how do I measure such a thing? And how do I come up with a law for working out this force? Because there's got to be some mathematical interpretation behind it, because nature doesn't work just in random fashions. There's got to be some kind of law or some physical meaning we can draw from this. So what he designed an experiment which in the book I think looks horrendously confusing. So what we have on the bottom, it's horrendously complicated now. I think my drawing is just going to be horrendously bad, so I know which is better. So he sort of had a dome on the bottom here, sort of a circular object, and in this circular object out the top he had sort of like his base thing that he had coming up here, and then he had on the top of this stick this was called a torsion head on the top, and he had a little thing that extended, and on this thing that extends he had what's the ball called? Oh, this is a bit bad. I always get the name of this wrong, and I didn't want to get it wrong. Pith. I want to keep saying pitch, that's why. So it's a pith ball. It's more of a triangle thing of mine, but he had a pith ball, and it sort of comes out of here. You don't need to know too much about this, it's just sort of introduction. So it's a torsion head, and then a little sort of metal thing that comes out of here, but you don't need to know. Basically it was on a string, and it's attached this pith ball, and then underneath here we've got, so attached to not attached to this turning, but he had another ball under here, and obviously this goes a bit lower, but this was just for emphasis. And basically these two balls, they touch. So should do it a bit more neatly. So they touch, but how they touch and what that does, I'll say that in a minute. Okay, so that's the basic diagram there. That is the essence of the diagram. But we need to be able to explain this diagram. So this is the apparatus that he came up with. I'm just going to make sure you can see it. I know you will be able to if you can. So that was the apparatus there. Now, obviously, they're not just, you can just pull this out of thin air. So how do we relate this to our idea of, because what he was trying to demonstrate in this experiment, he was saying, trying to demonstrate the force and how to work out the force between two charged objects. So this pith ball on the top, pith ball 1, and I'll just put PB2 on the bottom, pith ball 2. For pith ball 1, he charged this he just charged it with some, just charged it somehow in whatever way you would charge it. Sorry, he charged it back then. Assuming it's going ins and outs. You just imagine that's charged, and then these two balls touch. So, and then they touch with the other pith ball. So what does this do? Well, obviously if they touch, it transfers its charge. Oops, sorry. So it transfers its charge. And then when it's transferred to this charge, so this is now charged, that's charge has been annihilated, it's been forgotten, it's transferred to this PB2, pith ball 2. And then this pith ball 2, so I'll put PB2, repels pith ball 1. Because it's got now an opposite charge to pith ball 1. Okay? So obviously it shows it's conductor, etc. But the main thing is a touch and it's passed on the charge. Now this obviously creates, obviously that repels a pith ball, so that's some kind of force, isn't it there? Obviously. But in this string, so that's what it is, sorry, it's a string, it sort of twists. So then this causes, this is counteracted, counteracted. So basically they work against each other, is what I'm saying. Counteracted by the twist in the string, or twist in the wire or string. String/wire. So, obviously, if it counteracts, they don't move. So they don't move. But how can we change this? Okay, so they don't move. But if we change this torsion head, we're changing sort of the twist in the string, so we can reduce it. So basically, all you need to surmise from this is so they don't move because the repulsion here is counteracted by the twist in the string, because obviously they're repelling each other, and it causes a twist of string. So they don't move. But we can cause but if we change the torsion in the torsion head, we can set a distance. Obviously these two pith balls, by the way, they're meant to represent point charges. So obviously we'll go into that in the next video. Basically just a point charge, for what we're concerned with. But if we change a torsion in the torsion head, we can set a distance between the objects. Now, obviously, you can't just, I'll just turn it a little bit, turn it a bit more. There's got to be some maths behind this. So, the force we need to turn the torsion head creates us a distance. Now, I'm just going to rub this a little bit out here and move it down a little bit. So I'll give myself some space up here to put some figures. So charged, and then that touches PB2. There you go. Okay, so I'm just going to write some figures up here that Coulomb got. So all this is idea of measuring the force and how that acts with the distance. So that's the whole point of that experiment there. So as I said, basically this ball becomes charged, touches this one, transfers its charge, this repels it and builds up some twist in the string, which is counteracted by the repulsion of the charges, So they don't move, but you can change the torsion head to make them move, and the other two have to put some kind of force into this torsion head to create a distance. And we measure the distance with the force that's been applied to create this distance. And then we can look at these values and decide what we want to do. Okay, so I'm just going to put these values in. So this is R is the distance. So 36, 18 and 9. And then the force F, so for 36 it's 36 newtons. For 18 it's 144. And for 9 it's 567. Okay, so basically this is the force that's been applied and this is the distance that has been achieved. So if we look at them figures, what do we notice? Well, what we should notice is when we halve the distance from 36 to 18, we 36 has been times by 4, so the force has been increased by a factor of 4 when we so when we halve the distance we increase the force by a factor of 4, and that happens again. So we halve the distance and we increase it by a factor of 4. 36 times 4, 144. 144 times 4, 567. That's actually 8.5, but I've rounded it to 9 because it's pretty much 9. So that's why in some books you might not see it's 9, it might be 8.5, but irrelevant. So basically this is halving and this is increasing by a factor of 4. So what does that tell us? Well, that tells us that the force is proportional, directly proportional to 1 over r squared, to r squared being the distance. Now, how can we formulate this into some kind of formula? So, when we have a directly proportional, we have to have a constant of proportionality. So we have the F, and we're going to call this constant proportionality K. Now we need to have 2 point charges. So on the top is Q1 and Q2, and then we leave the r squared on the bottom, and that is essentially Coulomb's law. So basically you see how we've used these figures here to create this rather dastardly looking equation, and then formulated this. Now the only thing we don't know in that, assuming we know the distance and the charges, is what K is, the constant proportionality. Now K is equal to 1 over 4 pi times e to the 0. Now e to the 0 is not just anything, it is a permeability of free space, which is 8.85 times 10 to the minus 12 femtometers. Force per metre, sorry. And that is 9 times 10 to the 9. So K is 9 times 10 to the 9, but you can work it out just from inputting this. K is equal to 1 over 4 pi times e to the 0, the permeability of free space. So that's what we've got here in this formula. And then we just apply this formula to different values that we want to find out. Okay, so that's the main area of today's studies. So basically, just to recap, we had the Coulomb's law, which Coulomb thought, how do I demonstrate the force between 2 point objects? Because obviously there's some kind of force action between these two. They don't know they're oppositely charged. So it's sort of like exchange particles, if you kind of think of it like that. But obviously, you don't got the particle bit, it's just the electric force charges. And he said, oh yes, how could we possibly, is there any way I could be more sad and come up with an experiment rather than go out and get some friends and drink some lovely wine? You wouldn't be remembered for that. But so what he did was he thought, I'll create 2 pith balls. I'm not sure what these pith balls are, but just could be anything. Could be French for potato farms. But he thought, we'll charge one of these up and put it over this other. The other one hasn't been charged, and we'll put a little torsion beam so we can alter the force that's applied, because the build up in the twist of the string or the wire is actually counteracted by this repulsion of the forces between the 2 pith balls that you can see on the board there. And obviously that causes it to stay the same, but we can change the torsion. Oh, I was trying to avoid saying that the whole video. And if we change the torsion, we can sort of work out, we can alter the distance between the two. And as you can see from the results on the top right hand side of the board there, we've got a factor there. So when we halve the distance, remember, we increase the force by a factor of 4. So you could create any results, that's the idea. But just create some results there, just to show you the principle. And then from these results, we worked out that rule that when you distance halves, so when you distance halves, your force quadruples. We worked out as a constant proportionality there. Simplify that down, create an equation, and then obviously k. You don't need to really work out why k is that, but that was just to help pre-build up to the equation. As I said, only really interested in that is equation at the bottom there. So that's a quick overview of 5.4. Now I'm not going to go into any summary questions, purely because I don't want to waste too much of your time and try and keep my computer space down. But obviously, for your education, etc. Now, one more thing. Okay, so if you've got that, great. This last little bit of the video is just so you can say a bit more, a few minutes revising, or watching my videos, or you can turn off now because this is just a bit of again, background knowledge to science. So more of a chemistry thing, really. You may have sat in your room and wondered, why do salt crystals dissolve in water? I mean, I personally be wondering why don't you have some more friends, but if you've ever thought that, I'm going to explain it now. Basically, salt crystals have your sodium and your iron. Basically, they're oppositely charged, and when they're put in water, the water dissolves. These water breaks down the electrostatic forces between them, and then obviously they break apart, and then they slowly dissolve as you put your energy into stirring your little cup. So that's a little introduction, a little overview of why they dissolve. You don't really need to know that. I mean, as I said, the key things on the board is behind me, as we've got there. So the main thing was understanding why Coulomb came up with that law and how he came up with it, and how we can apply it to the results that we've got. Obviously, you can create some more results, but as long as they follow that pattern of halving the distance, the force quadruples, you can formulate that equation from any set of results you can come up with. Obviously, if you were to do this experiment, that's the kind of results you should get. But if you were like me and I tried to do that, I'd probably mess it up and get one result about 10,000 times off. But obviously I'd spot there's an anomaly, etc. So hopefully that's been a little bit helpful. If you do want me to go through the summary question for 5.4, or if you just want me to do some questions for those that you don't have the book, please do let me know. I mean, I just wanted to do a quick overview, really. I didn't want to waste go on too much, because this topic is this subtopic, is more about learning Coulomb's law and why he came up with it, why he came up with it, but how he came up with it even, and just understanding the sort of ins and outs of the experiment, really, and being able to derive that equation from, rather than me just saying mathematically, here's the equation, apply it to some questions, because that's all the summary questions are, really, just applying that force between the 2 point objects, and using it to just create the. Obviously, you could manipulate that into rearranging it, for example. But as I said, key bits are there. I mean, that's what you more or less be asked about. You're not likely to be asked, "Oh, Coulomb came up with this experiment. Please explain it and do a diagrammatic analysis." That is just purely there to represent what it looked like. But as I said, thanks for listening. I haven't gone too much at the end there. But I hope it's been helpful, and said any questions or comments, or if you want me to go through some questions, just please do leave me a comment, and we'll look forward to seeing you in the next video. Thanks for watching.